Hi students, how are you? My name is A.Roja Rani, working in K.G.B.V Gangavaram. So, in present 10th class, we can first chapter discuss about the real numbers. So, first chapter real numbers. So, already we can learn about the real numbers, the Euclidean division lemma and fundamental of arithmetic. Then find the LCM and HCF in the previous class. In present class, we can discuss about the rational numbers and decimal explanation. So, what is the rational numbers? So, we learn about a number which can be form of a p by q, p and q are any integers, q is not equal to 0. Our numbers are called a rational numbers. So, rational numbers. So, rational numbers we can represent on the capital Q. Capital Q. So, rational numbers we can represent on the capital Q. These numbers are called a quotient numbers. So, these numbers are called a quotient numbers. Then, can you expect any number between the 0 and 1? 1 and 2. 1 and 2. So, can you expect 0 and 1 and 1 and 2? So, these numbers are called a rational. These numbers are called a rational. So, in a 9th class, we can study a rational numbers can be expressed in the p by q, either terminating decimal expansion and non-terminating decimal expansions. In this section, we can learn about we can discuss about the rational number, say the p by q, and explore the exactly terminating decimal expansion and non-terminating decimal expansion. So, terminating means the end with the 0. Non-terminating decimal means there is no end with 0. So, first of all, let us some example. So, we can take some example we can discuss about. So, first of all, take a example. So, decimal form expressed in the rational numbers. So, 0.375. 0.37 is a decimal form. Then we can express the p by q. How? We can take a, so 375. We can write the denominator 1. How many places are, decimal places are there? 3 decimal places. Then we can put 3 zeros. 3 zeros. Then we can write the 375 by 1000 means how many zeros? 3 zeros. Then we can write the exponents form. That means 10 to the power of 3. Then we can take another example. Then 1.04. Then 1.04 we can write the 104 by how many decimal places? 2 decimal places. Then we can write the 2 zeros on the denominator. So 104 by 100 equal to 104 by 10 square. 10 square. Then take another example. 0.0875. So 0.0875. We can write the p by q form. Then 875 by how many decimal places? 4 decimal places. Then we can put the 4 zeros. So 875 by 1000 we can write the 10 to the power of 4. 10 to the power of 4. Next, another example we can take in 12.5. 12.5. So 12.5 we can written as a 125 by 10. So the power is 125 by 10 to the power of 20. So we can observe the all example. In observe all the terminating decimal expansion. So can we express the rational numbers when the denominator is a power of 10. Power of 10. So every rational number in a denominator is a power of 10. So let us now factorize the numerator and denominator. We can form a simplest form. We can convert the simplest form. How we can write the simplest form? So 375 10 to the power of 3 and 104 by 10 square and 875 by 104 we can write. So first one we can take a 0.375 is equal to 375 by 10 to the power of 3. So 375 we can find the prime factorization of a small division method. So small division method we can divide by the 5. 5 sevens are 35, 5 fives are 25. Next row 5 ones are 5, 5 fives are 25. Next row 5 threes are 50. So how many? So 5 into 5 into 5. 5 into 5 into 5, how many fives? 3 fives. We can express the 5 to the power of 3 into 3 by, then we can write the 10. 10 we can write the prime numbers 2 into 5. So 2 into 5 whole cube. So 5 cube into 3 by 2 cube into 5 cube. Then we can use the exponents. Loss of exponents a into b whole to the power of m. We can write the a to the power of m into b to the power of m. Then we can cancellation 5 to the power of 3 and 5 to the power of 2. Then we can write the 3 by 2 to the power of 3. So another example we can take it 1.04. That means 104 by 10 square. So 104 we can use the division method. So 104, 2 5s are, 2 2s are. Next 2 2s are, 2 6s are. Then take a 13 2s are. Then how many 2s? 2 into 2. Then 2 to the power of 3 into 13 5. So 10 we can write the 2 into 5 whole square. So 2 to the power of 3 into 13. But we can write the 2 square into 5 square. So we can cancellation the 2 square, that means 2 square. Then how many 2's? There are only 1 2. So 2 into 13 by 5 square. Then we can take another example. So 1.25 is equal to 125 by 10. Sorry, 12.5 take it 10. So 125 by, so 125 we can written as a 5 to the power of 3. 5 to the power of 3 by 2 into 5. Then cancellation the 5. Then 5 square by 2. Next, another example, 0.0875 is equal to 875 by 10 to the power of 4. Then 875 we can division the division method. 875 we can division the 5. So 5 ones are 5, 5 sevens are 35, 5 fives are 25. Then 5 threes are 15, 5 fives are. Next to 5 sevens are. Then we can write the 5 to the power of 3 into 7 by, we can write the 2 into 5 4 to the power of 4. Then 5 to the power of 3 into 7 by 2 to the power of 4 into 5 to the power of 4. Then 5 again cancellation. Then 7 by 2 to the power of 4 into 5. We can observe all the denominator. We can observe all the denominator which a decimal expression expands expressing the rational number say p by q. And when a denominator is a power of 2 or 5, power of 2 or 5 or both, power of 2 or power of 5 and both, because the power of 10 only write a product of 2 power of 2 or 5. So we can observe all of you. Then first of all 3 by 2 to the power of 3. Then second one 2 into 13 by 5 square. Then so 5 square by 2. Then 7 by 2 to the power of 4 into 5. So we can observe all the denominators. Power of 2, power of 5, then power of 2, then power of 2 or 5, both. So this is all terminating decimal. Take some example. Then we can write the 15,625 by how many decimal places? 3 decimal places. We can put the 3 zeros. That means 15,625 by 1000. We can write the 10 to the power of 3. Then another example 0.4. So 0.4 is written as the 4 by 10. So 4 by 10 to the power of 1. Then another example 0.125. Then we can write the 125 by 100. So how many zeros? So 3 zeros. We can write the 1000. 125 by 1000 is equal to 125 by 10 to the power of 3. So any real numbers which a decimal expression terminates. So can be decimal. Then you write the rational number p by q when a denominator is a power of 2 or power of 5 or both. Power of 2, power of 5 or both. Which can be written as the rational numbers. The prime factorization of q is form of 2 to the power of n. So 15,625 I can write the 2 into 5 whole cube. So that means 15,625 by 2 cube into 5 cube. Then 4 by 2 into 5. Then 125 by, then we can write the 2 into 5 whole cube. So 125 by 2 cube into 5 cube. So any real number, we can observe the real numbers which the decimal exponential. Which the decimal exponential is a terminate. Terminate means the end with the 0. So can be written as a rational number say p by q when a denominator is a power of 2 or power of 5 or both. So when it can be written as a rational numbers, the prime factorization of in the form of a p by q, the prime factorization of q is form of 2 to the power of m into 5 to the power of m. So we conclude on the theorem, then we can how to tell the theorem. Then x is a rational number. X is a rational number whose the decimal exponential is terminate. Decimal exponential terminates. So the rational numbers we can express the form of p by q. Q comma p comma qr is the co-prime numbers. The prime factorization of q is the form of 2 to the power of n and 5 to the power of m. So we can form of 2 to the power of n and 5 to the power of m. Where n comma m is a non-negative integers. Again we can tell the theorem. How to define the terminating decimals? Then x is a rational number whose decimal exponential terminate. The rational number is a form of a p by q. The form of a p by q. The form of a p by q. So where p comma q is a co-primes. P comma q is a co-primes. The prime factorization of a q is form of 2 to the power of n and 5 to the power of n. So where n comma m is a non-negative integers. Non-negative integers. So fine. So what is the terminating decimal? We can identify in a denominator. We can express the power of 2 or power of 5 or both 2 and 5. So you can understand. So power of 2 or power of 5, both 2 and 5. So this is the terminating decimal. So we can how to define. How to express the rational numbers form of a decimal form. So we can use the theorem or division method. So first of all we can take one example 25 by 2. So 25 by 2 is a, we can easily identify the terminating decimal. How? In the theorem, the rational number p by q. The rational number p by q. Whose the decimal expression terminate. In a p by q, q is a form of 2 to the power of n, 5 to the power of n. That means power of 2, power of 5 or both. So power of 2, then we can, the denominator is 2. So this is the terminating decimal. Then we can use the division method. So 2 we can divide by the 25. 2 ones are 2. Then we can divide the 5. Then how many times? 2 twos are 4. So 5 subtraction the 4. The remainder will be 1. So then we can 1. Put the point, decimal point. Then we can 0. Then 5 twos are 10. So the remaining with the 0. Then 25 by 2 is the decimal point is 12.5. Then we can use the theorem. 25 by 2. So in a denominator, every denominator we can form a 10, 100, 1000. We can change into 10, 100, 1000. Then we can easily put the point. So we can multiply the both numerator into denominator 5. Then 25 5s are 125. Then 5 2s are 10. 5 2s are 10. Then how many zeros? 1 0. We can put a 1 places on the right side. Then 12.5. So we can do. So both are answer equal. Then division method and we can use the theorem. Then another example we can take it. Where 3 by 8. 3 by 8. Then we can division the 8. 3 by 8. Here numerator is a 3, denominator is a 8. Then we can put a 0.0. So 8 3s are 24. Then we can subtract the 30, 24. Then 6. We can put a 0. Then 8 7s are 56. 8 7s are 56. Then subtract the 60 minus 56. Then the will be 0. Put the 0. 8 5s are 4. So we can use the theorem 3 by 2. 8 we can replace the exponents from 2 to the power of 4. So 2 2s are 4. 4 2s are 8. So 2 to the power of 3. Then we can multiply the power of 5. So we can multiply the power of 5. So this is the denominator is like 2 to the power of 3. So we can multiply the numerator and denominator 5 to the power of 3 by 5 to the power of 3. So 3 into 5 5s are 25. 25 5s are 125 by. So 2 into 5 whole cube. Then 3 5s are 15, 3 2s are 6 plus 7, 3 1s are 3 by 5 2s are 10 whole cube. So 375, 10 cube means 10 into 10 into 10. Then we can write the 1000. How many zeros? 3 zeros. Then we put a point and 3 decimal. 3 values on the before. That means 0.375. So we can understand. We can use the theorem and division method. So next, in a textbook, do this. You can practice. So this is also terminating decimal. Then we can identify the in a p by q. Q is the comma, power of 2, power of 5 or both. Then we can take a non-terminating recurring decimal. Non-terminating recurring decimal. So how to non-terminating recurring decimal we can find? So take a one example. 1 by 7. 1 by 7 we can divide the 7. So 0.0. 7 ones are 7. Then we can take a 3. We can put a 0. 7 fours are 28. So we can subtract the 30, 28. That means 2. Put a 0. 7 twos are 14. Then we can 20. Subtracted the 14, 6. Then put a 0. 7 8s are 56. Say 4 and 0. So 7 5s are 35. 35. Then 5. Put a 0. Then 7 7s are 49. Then remainder 1. So 1 by divide we can express the decimal form 0.1287. Then we can repeat at the 1. So there is not ending with the 0. The division will be continuation. This is the non-terminating repeating decimal or recurring decimal. So in here we can see in a denominator 7 we cannot express in the form of 2 into 5. So we cannot write the prime numbers 2 into 5. So 7 we cannot write as a 2 into 5. So this is a non-terminating recurring decimal. So then another example 1 by 3. So 1 by 3 is we cannot written as a 2 into 5. So 1 by 3 is also a non-terminating repeating decimal or recurring decimal. Then we can divide the 1 by 3. So 0.0. 3 3s are 9. 1 0. 3 3s are 9. 1. 3 3s are 9. So 1. So we can 1 by 3 we can repeat at the 0.333. We can use the bar 0.3 bar. This is a non-terminating repeating recurring decimal. So how to decide? Then x is a rational number such that the rational number, the prime factorization of 2 is not form of 2 to the power of n and 5 to the power of m. So this is a non-terminating repeating decimal. So what about in a denominator we cannot written as a 2 to the power of n and 5 to the power of n. So this is a non-terminating repeating decimal. Then x is the rational numbers such that the prime factorization of q is not form of a 2 to the power of n, 5 to the power of m. Where n comma m is a non-negative integer, there is a decimal exponential which is a non-terminating repeating decimal. So we can take some example without actual division how to identify the terminating decimal and non-terminating decimal. So how to we can find the terminating decimal and non-terminating without division method. So we can take a 16 by 125. So 16 by 125. 125 we can written as a 16 by 5 to the power of 3. 5 to the power of 3. 5 5s are 25, 25 5s are 125. Then we can write the 5 to the power of 3. So what is the terminating decimal? In a rational number form of a p by q, q is a form of a 2 to the power of n and power of 2, power of 5 or both. So any other number we cannot division. So power of 2 and power of 5, both 2 and 5. Then any other, suppose 7, 3, any another, we cannot take terminating decimal. So 5 to the power of 3. So 16 by 5 to the power of 3. Then power of 5. This is the terminating decimal. Terminating decimal. So take another example. 32 by 18. So 32 by 18. 18 we can write and say. So 18 means 2 9s are 3 3s are. So 2 into 3 square. 2 into 3 square. So in a p by q, q is form of a power of 2, power of 5. Both 5 and 2. So we can take another. What is 3? Only 2 or 5 and 2 and 5. So again another number, then 3 square. So this is not a non-terminating repeating decimal. Non-terminating repeating decimal. So we can 2 1s are 2 16s are. Then 12 by 3 3s are 9. Then we can division the 9. 9 1s are 9. 12 9 is subtraction the 3. Put a point 0. 9 3s are 27. Then we can take a 3. So 0 3. 27. Though 1.33 also. Then we can expect 1.3 bar. So this is a non-terminating repeating recurring decimal. So we can discuss about the exercise 1.3 sum. So exercise 1.3. Write the following rational numbers in their decimal form and also state which are the terminating and which have a non-terminating repeated decimal. So we can take some example. We can how to prove this statement. First of all, taken 1.3. So write the following rational numbers in their decimal form and also state which are the terminating decimal and non-terminating decimal. So we can take one example, 8 by 125. So 8 by 125 we can written as a 8 by 5 to the power of 3. So in a denominator, we can numerator and denominator we can multiply the 2 to the power of 3 into 2 to the power of 3. So 8 into 2 2s are 4, 4 2s are 8 by 5 into 2 whole to the power of 3. So 8 8s are 64, 5 2s are 10 whole to the power of 3. Say 64 by how many zeros? 3 zeros. Then we can put a point 3 places only before 0.064. Point 2 3 places. So 0.064 is a terminating decimal. 64 by 1000 is equal to 0.064. Then 125 we can division the 8. So 0.000. Then we can take a 6. 6 5s are 33. 6 2s are 12. 12 plus 5, 15. 1 6 1s are 6 plus 7. Then we can 50. Put a 0. 4s are 5 4s are 20. 5 2s are 8 plus 2. 10. 4 1s are 4. The remainder will be 0. So 0.000. 0.064. So decimal form is 0.064. So there is a terminating decimal. So another exercise 1.3, take a second Roman. Without performing division, state whether the following rational numbers will have a terminating decimal form or non-terminating repeating decimal form. So take a one example. So 29 by 343 without a performing division. So without a performing, say 29 by 340 we can written as a 7 to the power of 3. 7 to the power of 3. So 7 to the power of 3. So in a p by q form, q is a form of a 2 to the power of a into 5 to the power of a. That means power of 2, power of 5. Other than, so then both 5 and 2. So you remaining any number, it is not a terminating decimal. This is a non-terminating repeating decimal. Non-terminating repeating decimal. So take another. So 23 by 2 to the power of 3 into 5 square. So we can see the denominator power of 2, power of 5. This is the terminating decimal. So we can, for terminating decimal, we can express the decimal form 23 by 2 cube into 5 square. This is the power of 2 to the power of 3, 5 to the power of 2. Then we can both multiply the 5 in numerator and denominator 5. 5 3s are 15, 5 2s are 10 plus 1, 11 by 2 to the power of 3 into 5 to the power of 3. Then 115 by 2 into 5 whole cube. So 115 by 5 2s are 10 to the power of 3. Then 115 by, so how many zeros? 10 to the power of 3 we can write as 10 into 10 into 10. That means 1000. Then how many zeros? 3 zeros. Then we can put on the point and the 3 places in the right side. Then 0.115 is a terminating decimal. Next, we can, so all of you understand? In exercise 1.2, we can write the remaining problems. Next, another topic is irrational numbers. So irrational numbers, a number which cannot be written as a p by q, where p comma q is a integers, q is not equal to 0. So these numbers are called a irrational numbers. So irrational numbers, what are they? Irrational numbers we can represent as the q dash and s. Q dash and s. So in irrational numbers we can represent as the q dash and s. So the example, root 2, root 3, root 5, root 11 and so on. So we cannot, n is a natural number. There is not a perfect square. There is not a perfect square. These numbers are called a irrational numbers. So irrational numbers in the previous class, in 9th class, how to locate the number line. How to locate the number line. However, we did not prove that a number is a irrational number. In present section, we can prove the root 2, root 3, root 5, root 7 is a irrational number. So how to prove the root 2, root 3, root 5, root 11 is a irrational number. A number is a irrational number. We need to follow the statement. What is the follow the statement? So we can prove the root 2, root 3, root 5, root 11. We can follow the statement. So what is the statement? Let p is a prime number. P is a prime number. P divides a square. where A is a positive integer. Positive integers. P divides A. P divides A. This is a statement. So, let P is a prime number. P is a prime number. Already we know that the prime numbers, 1 and itself is the factor. That numbers are a prime numbers. P divides the A square. P divides the A square. Where A is a positive integer. Then P divides the A. Then P divides the A. So, how later prime factors of A. So we can take A is equal to P1 comma P2 and so on Pn. Then we can square in the both sides. A square is equal to P1 P2 and so on Pn whole square. So A square is equal to P1 square P2 square and so on Pn square. So A square is equal to P1 square P2 square and so on Pn square. So what is we can observe? P divides the A. P divides the A. We can use the fundamental theorem of arithmetic. What is the fundamental of arithmetic? Every composite number can be expressed the product of primes and factorize the unique part of order which can be primes or accused. So every composite number we can express the product of primes. We can observe it is although the P is the one of the prime factorization of A square. One of the prime factors of the A square. So P is the only prime factors of the P1, P2, P3 and so on Pn. So P is the only prime factors of the A square. That means P1, P2 and so on P. So P is only one of the P1, P2, P3 and so on Pn. So A is equal to P1, P2 and so on Pn. So P divides A. So another we can explain. Let P is a prime number. P divides the A square. Where A is a positive integer. So P divides and also P divides the A. So let A prime factors of the A. Then A is equal to P1, P2 and so on Pn. So A square is equal to P1, P2 and so on Pn whole square. Then A square is equal to P1 square, P2 square and so on Pn square. So P divides the A square. What is the fundamental arithmetic theorem? So every composite number we can express the product of primes. So P is the only prime factors of the A square. So P is one of the number of A. P1, P2 and so on Pn. So A is equal to P1, P2 and so on Pn. So P divides the A. Then we can use the statement. We can prove the irrational number. First of all, we can show the root 2 is the irrational number. First of all, we can prove root 2 is irrational. So first of all, we can let us assume root 2 is a rational. This is the contrary. What is the contrary? We can prove the irrational number. We can assume the rational numbers. So we can take a rational number. We can solve the problem. Then we can conclude this is the irrational. We can prove the irrational number. That is the contrary. So first of all, let assume root 2 is a rational number. It is a rational. There must exceed 2 integers R and S. Then we can write as root 2 is equal to R by S. R by S. If R and S is a common factor other than 1. Other than 1. So we can divide the common factor. We get a root 2 is equal to A by B. Root 2 is equal to A by B. Where A and B is the co-primes. B is not equal to 0. B is not equal to 0. So we can cross multiplication root 2 B is equal to A. Squaring the both sides. So root 2 B whole square is equal to A square. Then root 2 B square is equal to A square. We can see that 2 divides the A square. 2 divides the A square. And 2 divides the A. So 2 divides A square and 2 divides A. Then we can take A is equal to 2C. Why we can take a 2 into C, then we can multiply up the 2. So A is equal to 2C. Then we can substitute the place value of 2C. Then we can write the 2B square is equal to 2C whole square. Then 2B square is equal to 2 2s are 4C square. Then we can cancellation 2 1s are 2 2s are. So B square is equal to 2C square. Then we can multiply. So 2 divides the B square and 2 divides B. 2 divides B. So both are, therefore both are A and B. 2 is the common factor. 2 is the common factor. But contradiction fact A and B is the co-prime numbers. A and B is the co-prime numbers. So A and B is a co-prime number. The contradiction fact reason root 2 is a, in our assumption, root 2 is a rational number. So let we can observe our assumption root 2 is a rational is a false. So root 2 is a irrational number. Root 2 is a irrational number. So another we can explain. So how to prove the root 2 is a irrational number? So root 2 is a irrational number. Let us assume that root 2 is a rational. This is a contrary. So contrary means we can take a opposite. So we can prove that the irrational numbers we can take a rational numbers. So root 2, it is a rational number. There must exist 2 integers. So R and S. Then we can express root 2 is equal to R by S. If R and S is a common factor other than 12. So we can divide the common factor. We get a root 2 is equal to A by B. Where A and B is the co-primes. B is not equal to 0. B is not equal to 0. Then root 2 is, you can cross multiplication. Root 2 B is equal to A. Squaring the both sides. Root 2 B whole square is equal to A square. Root 2 into root 2, 2. B into B, B square is equal to A square. So we can observe 2 divides the A square and 2 divides the A. So take A is equal to 2C. We can substitute in the equation number 1. So A is equal to 2C, then 2B square is equal to 2C whole square. So 2B square is equal to 2 2s are 4, C square, 2 1s are 2 2s are 4. Then B square is equal to 2T square. We can observe the 2 divides the B square and 2 divides the B. 2 divides the B. So we can observe the both are A and B is the 2 is the common factor. 2 is the common factor. The contrary A and B is the co-prime number. The contradiction of the horizon, let our assumption is root 2 is a rational number. So let a root 2 assumption is a false. So root 2 is a irrational number. So we can take another example. You can follow now. can solve in this process. We can take a root 3. So another example, we can take a root 3. Prove the root 3 is a rational number. Say, let assume root 3 is a rational number. Root 3 is a rational number. So root 3 is equal to a by b, where a comma b is the co-prime numbers. We can cross multiplication. Root 3 b is equal to a. So squaring the both sides. So root 3 b whole square is equal to a square. Root 3 3. B square is equal to a square. Then we can observe 3 divides the a square. 3 divides a square and 3 divides a. So take a is equal to 3c. We can substitute the a value in 3c. 3b square is equal to 3c whole square. So 3b square is equal to 3 3s are 9c square. 3 1s are 3 3s are. Then b square is equal to 3c square. Then we can observe 3 divides the b square and 3 divides the b. So 3 divides b square. 3 divides b. So we can, therefore, both a and b is a 3 is a common factor. 3 is the common factor. First, contrary, we can a comma b is the co-prime numbers. So our contrary is root 3 is a rational number. This is the wrong. So root 3 is a irrational number. So we can follow this process. We can prove the root 5, root 7, root 11. So then we can take another example. 5 minus root, prove the 5 minus root 3 is a irrational. Say, we can take let us assume a root 3, 5 minus root 3 is equal to rational number. First of all, let assume a 5 minus root 3 is a rational form. So 5 minus root 3 is equal to a by b, where a comma b is a co-primes, b is not equal to 0. So we can translation the 5, then my a. So plus a by b we can transfer in the other side. We can a minus a by b is equal to minus root 3 we can transfer in the RHL. Then we can change the plus root 3. Then we can take a LCM. 5 into b, 5b minus a is equal to root 3. Then we can write the root 3 is equal to 5b minus a by b. So we can observe where a comma b is the integer. A comma b is the integer. So 5b minus a by b is a rational. So 5b minus a by b is also rational numbers, and also root 3 is a rational number. But contradiction, root 3 is a irrational number. So root 3 is a irrational number. So 5 minus root 3 is also a irrational number. So you can understand. Then prove the 5 minus root 3 is a irrational number. 5 minus root 3 is equal to a by b, less than the rational number. Then we can transfer in the LHS to RHS. 5 minus a by b is equal to minus root 3, transfer in the RHS plus root 3. Then we can take LCM. 1 into b, b. 5 into b, 5b minus a by b is equal to root 3. Where a comma b is the integer. A comma b is the integer. So 5b minus a by is a rational number. So 5b minus a by b is a rational number, and also root 3 is a rational number. But root 3 is a irrational number. So 5 minus root 3 is a irrational number. So next we can take another example. Root 2 plus root 3. Root 2 plus root 3. So let assume root 2 plus root 3 is a rational number. So we can transfer in the Root 2 is equal to a by b. We can transform the plus root 3 in RHS, then minus root 3. So squaring both sides. Squaring both sides. Squaring both sides. So root 2 whole square is equal to a by b minus root 3 whole square. Then we can cancellation the square root 2 is equal to, we can use the a minus b whole square. Then a square, that means a by b whole square minus 2ab. 2 into a by b into root 3 plus root 3 whole square. So 2 is equal to a square by b square minus 2a by b. 2 into a by b root 3 is equal to root 3 cancel. Then we can transferring the minus 2 into a by b into root 3 in the LHS. Then 2a by b, 2 into a by b root 3 is equal to a square by b square plus 3. Then plus 2 we can transfer in the RHS, then minus 2. So 2 into a by b root 3 is equal to a square by b square. We can subtract in the 3 minus 1, then 1. Then take a b into b square into 1 b square LCM. We can cross multiplication 1 into a square 1 a square plus 1 into b square 1 b square. Then 2 into a by b into root 3 is equal to a square plus b square by b square. Then 2 into a by b we can multiply. We can transfer in the RHS, then division. Then root 3 is equal to a square by b square into b square by 2a. Then we can take a reciprocal. Then a by b we can reciprocal b by a. Then 2 is reciprocal 1 by 2. Then we can cancellation the pb. Root 3 is equal to a square plus b square by 2ab. We can observe the a comma b is the integer. A comma b is the integer. So a square plus b square by 2ab is the rational number. Rational number. So a square plus b square by 2ab is the rational number. So root 3 is the rational number. But contradiction, root 3 is a irrational number. So root 2 plus root 3 is also a irrational number. So observe root 2 plus another root 2 plus root 3 is equal to a by b plus 3 transferring the RHS minus root 3. Squaring the both sides. Root 2 whole square is equal to a by b minus root 3 whole square. We can use a minus b whole a square minus 2ab plus b square. Then we can transfer in the minus 2a by b root 3 in the LHS. So root 2 into a by b into root 3 is equal to a square by b square plus 3 minus 3 subtraction the 1. Take LCM 1 into b square. We can cross multiplication a square plus b square. So 2 into a by b we can multiply, then we can transfer in the division. A square plus b square by b square into b by 2a. We can cancellation b cancellation. Then a square plus b square by 2ab. A square plus b square by 2ab. A comma b is the integer. So a square plus b square by 2ab is the rational number. So a square plus b square by 2ab is a rational number. Root 3 is also a rational number. But contradiction, root 3 is a irrational number. So root 2 plus root 3 is a irrational number. So give the assessment. So root 5, root 7, root 11. Irrational numbers. Next, sixth place, root 3 is irrational. Root 3 plus root 5 irrational number. So this is the assignment. All our students, we can listen the irrational numbers and we can solve these problems. First, I will recall some points. First of all, rational numbers and decimal explanation. So terminating decimal, non-terminating decimal. How to identify the terminating decimal? In a rational number p by q, q is the form of a 2 to the power of x, 5 to the power of f. That means power of 2, power of 5 or both 5 and 2. So this is the terminating decimal. So in a p by q form, q is not a form of a 2 to the power of x, 5 to the power of f. So this is the non-terminating decimal. So which cannot be written as a power of 2, power of 5. This is the non-terminating decimal. This is the 2 points we can understand. Then we can prove the how to irrational number. So we can statement let p is a prime number. P divides the a square and p divides the a. Where is the a is the integer. This is also a assignment. Then we can all our students can write down in your notebook. Thank you.